Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Reinforced Soil Structures Design and Facing Systems. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and elders past, present, and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Geofabrics. Geofabrics is Australasia's geosynthesis specialist. They help their clients deliver and maintain infrastructure by minimising risk and increasing value through the innovative use of geosynthetic products. Geofabrics have supported the Australasian infrastructure sector on significant projects from the Victorian level crossing removal to APLNG in Queensland and the Christchurch gondola also in New Zealand. On these projects and every project they undertake, they have a singular focus to provide smarter infrastructure solutions. Today, you will hear from 3 speakers, followed by a live audience Q&A, and I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to welcome our first speaker, Alan Garrard. Alan is a Senior Principal of CMW Geosciences, a specialist geotechnical consultancy, and has over 35 years' experience in civil and geotechnical geological engineering, spanning the planning, design, management and site supervision of many diverse projects. Alan has provided technical verification of many large projects, both nationally and internationally, and is called upon to provide expert witness services. Please welcome Alan Garrard.
Thank you for the introduction. Today we're going to talk about reinforced soil structures and facing systems. My part of the presentation is mainly concerned with design issues and mechanisms of failure for reinforced soil structures and facing systems. So this is the agenda. So I'm going to go through some design aspects of reinforced soil structures. And as I say, using Australian standard for retaining wall systems to talk about mechanisms of failure, and then Geofabrics will follow. So reinforced soil isn't a new concept at all. It's been used over hundreds and even thousands of years. The Romans were into reinforced soil structures, and there's plenty of evidence of that around the world. I was first involved in reinforced soil structures in the mid-80s when it was quite new in the UK, and we designed different types of reinforcement in soil structures and instrumented them to convince the road authorities at that time that these actually worked. So modern reinforced soil structures really came about through the advent of plastics, high strength plastics. So it was a breakthrough in innovation at the time, early to mid 80s, and has been used extensively throughout the world since. The greatest attraction is the versatility of these types of structures, and they can perform under extreme loads and have the ability to reach great heights. Asia is a good example of reinforced soil structures where designs have gone up to 60, 100 meters or more. And there's some examples there in the photographs. So also through time, reinforced soil structures have become much more cost effective compared with other types of retaining walls. And this is a graph from Corner et al., which indicates that after around 4 meters retained height, reinforced soil structures become hugely cost effective, and especially that cost effectiveness increases with height. So these are the components of a reinforced soil wall. You've got some sort of facing element, and there are a huge number of examples of facing elements. And I've used many throughout my career. You've got the reinforcing element, which can be grid or high-strength geofabric. And then usually there's some sort of internal drainage system within the wall, and often behind the wall at the heel of the wall, to make sure that the wall doesn't experience loads from water seepage and flow. In the middle of the slide there, I've got a little cartoon which shows how a reinforced soil wall works. So if you look at that active wedge coming up from the toe of the wall, if the reinforcement wasn't there, the reinforcement and the facing weren't there, that active zone would be lying on the ground in front of the wall. What the reinforcement and facing does is allow that structure to be built vertically, and you can see in red is a depiction of the tension in the reinforcement element, which is fairly small at the facing and really only serves to retain a small wedge of soil between the reinforcing elements at the face, shown there in green. And then the tension climbs to around a maximum of around where the active wedge crosses through the reinforcement, and then the tension tails off towards the back of the reinforcement. There are many structures which utilize a combined facing. The example in the photograph there and in the sketch above shows a sort of gabion type facing for the bottom half of the wall, and that's to do with issues of erosion from flooding of the creek. And then the remainder of the wall can be a separate facing system. So that's quite common in practice. And this is a sort of real world example of how the reinforcement works. You can see the block facing at the front. The reinforcing elements are shown in red dotted lines, and the active wedge is shown in yellow there. And the reinforcement allows that wall to stand vertically. So one of the reasons why reinforced soil structures are so cost effective is that the vast majority of the reinforced soil structures are built from soil, and the reinforcement and facing is only a small part. So the actual materials required are very low in terms of their volume, and the reinforcement acts with the soil as a composite system. So how do we design with reinforcement? Well, we need to look at a number of mechanisms. On the left there, you'll see an internal stability mechanism where an active wedge, and that's an example of a two-part wedge, which is used by the Australian Standard. And that wedge can either break the reinforcement or allow the front of the wedge, the material in front of the wedge, to pull out, so the reinforcement to pull out from the soil. So these checks have to be made with all the loading applied and with the correct geometry. And sometimes it's an iterative process to get the geometry right and the spacing of the reinforcement correct. On the right there, you'll see the external stability checks which need to be done. So the wall is considered as a block type element, and there's got to be checks made on overturning, sliding, and bearing capacity. But also what's not there is global stability, where a circular or non-circular failure could develop around the wall, underneath, and exit at the toe or in front of the toe. So these are failure mechanisms directly from the Australian Standard, AS4678, earth retaining structures. So these are as shown in the standard. It's critically important if you're embarking on designing reinforced soils, in fact, any civil engineering structure, is to understand what the mechanisms of failure could be. And that's where I start when designing anything, is how could it fail? So these are examples given. So sliding at the base, sliding on one of the reinforcement levels, rotation about the toe of the wall, rupture of a connection, and it can be either an anchored connection or a connection where geogrid is wedged between two elements of the facing system, rupture of the reinforcement at the connection, and some sort of failure or rupture of the facing itself. Continuing with the failure mechanisms, there's also pull out of the reinforcement at the back of the wall, some sort of trapezoidism of the wall, which is akin to a type of overturning mechanism. There's the global, top right is the global stability that we talked about, and that can be either a circular or non-circular failure, and the failure envelope can exit at the toe of the wall or even well in front of the wall. Bottom left is bearing capacity failure. Bottom middle is rotation of the face, which could occur if the reinforcement is too extensible. And bottom right is some sort of translation of the facing. These are the last two in the Australian Standard, bulging of the facing and settlement of the reinforced soil block itself. So now we'll talk about some examples from practice that I've been involved with and others that I know have been involved with, and comparing these actual examples of failure mechanisms to those that are depicted in the Australian Standard. So on the left there, this wall has suffered sliding at the base, and there's a little bow wave in front of that wall, which is difficult to see, but it is there. And there is a separate and possibly um, uh, a mechanism that's possibly combined is global is sliding and global stability. So on the right there, you can see tension cracking at the back of the wall. The wall's underneath that speed bump. So the wall is possibly rotating as well as sliding forward. And also some bulging happening on the face. So that's multiple mechanisms for one wall. This is an example of where the wall has failed in sliding on one of the reinforcing elements. So that needs to be checked as part of the internal stability analysis. This one has failed in bearing, so the wall has been built on clay which is too soft and has suffered a bearing capacity failure adjacent to the creek. This wall is a bridge abutment. The wall is off and down to the right, but it's failed in global stability, where the wall has rotated, and that bush is growing out of the major tension crack that has occurred in the road. This is another example of global stability, but in the previous case, the failure envelope exited well in front of the toe of the wall. In this case, the failure plane or failure envelope exited near the toe of the wall. Here's an example or two examples where the reinforcement connection has ruptured, allowing the facing to spill forward. And that's, although it's not a catastrophic failure, it's certainly something that needs to be fixed. And this one here is more on the construction side of things. The previous failures were more about design issues. This one is where the reinforcement wasn't long enough. In fact, was curtailed by the contractor because of a whole load of services that had to be placed in the back of the wall. So the contractor hadn't been talking to the designer about whether it was possible to curtail reinforcement at the back. And the sketch on the right-hand side is one I was involved in many years ago, where the design length of reinforcement wasn't achieved because the contractor didn't understand what the reinforcement was doing, why it was necessary, and skimped on the excavation. And so the reinforcement wasn't, although the reinforcement was the right length, it wasn't placed in the right spot. So the reinforcement was just led up the slope, and we dug forensic slots into this wall to find that this was the case. So the other category of failures is, or the main category is drainage issues. So we've had design issues, construction issues, and drainage issues. And drainage issues, you could say, is probably mainly a design issue, but could also be a construction issue, and could be a temporary works issue, because the wall on the right failed during construction with insufficient drainage to avoid the development of sinkholes after heavy rain. The one on the right is mainly about erosion, where the reinforcement's been exposed by excessive erosion. And this is an example from my own experience fairly recently. This is a 27-metre high reinforced soil wall built in Queensland, Australia. And we used the TerraMesh system with a gabion front and TerraMesh tails and a main Paralink reinforcement system. This wall caters for heavily loaded large mine trucks, as well as being as high as it is, and hasn't suffered any movement at all from the monitoring that we've done. So this shows that these types of walls can be built to very high and to cope with very large loadings. And the beauty of them is that they have a flexibility to cater for large loadings and extremely high heights. Thank you.
Thank you, Alan, for a great presentation. I'd now like to welcome our second speaker, Eric Yu. Eric is a specialist engineer with more than 26 years of experience, including designing reinforced soil slopes and walls, slope rehabilitation works, slope stability analysis, and rockfall protection structures. One of Eric's assignments consisted of being part of the panel for the MBIE Rockfall Protection Structures Design Considerations Guideline. Since 2020, Eric has transitioned roles across Geofabrics Australia's slope and wall sectors technical BDM. Please welcome Eric Yu.
Thank you, Amanda. We're coming to the next sections of the presentation, which is the phasing system for reinforced soil structures. Before we talk about phasing system, let's revisit the essential components of reinforced soil structures, which are obviously the phasing system. We're going to spend time talking about it today. At the same time, we're going to also talk a little bit on the type of soil and the different different type of soil that is available for the type of reinforced soil structures, depending on the phase inclination. We don't have time to discuss in details on the type of reinforcement, options of reinforcement used in this presentation. And it's always good to know as a system, reinforced soil system, you probably want to allow for some internal drainage, always good to have. It is something that more of a precautionary measures to keep the reinforced soil structures dry. And before we talk about reinforced soil phasing system, these are the common factors when it comes to consideration on the type of phasing system. And they are obviously aesthetics. This dictates the final look of the structures to blend with the surroundings. The phase angle. Phase angle affect the type and suitability of the fill material specification. We'll cover that a little bit after this. The speed of installation also can be dictated by the type of phasing. Certain type of phasing obviously will be able to construct quicker than some other types. Situations such as emergency works that requiring speed, cost of labor, and etc. Location, depending on the location of where you are, some phasings may be readily available, so that dictates the consideration for phasings as well. Lastly, environmental. Some clients prefers a vegetative look, or some prefers a rock look, to blend with the environment. Obviously, all of that affects the entire cost and of the retaining structures. Now again, before we talk about phasing systems or options, it's probably fair to good to know that the demarcation or the determination of whether you're considering mechanically stabilized earth walls or the terminology used for any structures gentler than 70 degree is reinforced soil slopes. And as you can see from there, 70 degree is where internationally recognized. Beyond 70 walls, below 70 slopes. Some of the considerations or factors are that, for design guidance, there are more published guidance for walls compared to slopes. Lateral earth theory governs for external stability, typically for walls, whereas for reinforced soil slopes, the slope stability theory governs, and there are lesser published guidance on design for slopes. In terms of the connectivity or connection strength between the reinforcement to the face of the structure, they are much more important and critical for walls compared to slopes. Not that they are not important, but less demanding. And also the geogrid strength demand is greater, much greater for walls compared to slopes. They gradually diminish in terms of the demand from a steeper angle of say 70 degree to say a gentler angle of less than 1 in 2. Structural field, very important in terms of the quality of the field for walls. Some form of relaxation for slopes. And let's have a look at what design code says about them in terms of the soil field, soil requirement. And the first reference we can draw to and refer to is the Australian standard 46778 2002. You can see this similar cross-section diagram here where they have identified 70 degree as the demarcation for revetment structures and anything steeper than 70 degree retaining structures. And there are no further guidance provided by the standard in terms of the design for revetment structures. So we have to refer to other guidance when it comes to the design of reinforced soil slope structures, which is the American Federal Highway, whereby they mention for steepened slope up to 70 degree, the design should follow conventional slope stability analysis method. And they have identified 3 types of modes, which is external, which is overall stability, compound stability, somewhere in between internal and external, and obviously the internal stability, making sure that the structure is self-stable with the layers of soil reinforcement. And the reason for having slope stability method compared to lateral earth pressure theory is because of that particular diagram I showed on the top, whereby the donkey is lifted up due to the weight of the goods behind it, and this is represented by the pressure that is exerting at the rear of the block compared to the toe of the block, thereby the criticality of slope stability more so. When we talk about type of reinforced soil field, this is the specification given by AS 4678. The 2 most important parameters in this case are the plasticity index, which measures how clayey the soil is, shouldn't be more than 12. And then the fines content of more than 75 micrometers shouldn't be more than 15%. These are the 2 most important criteria when it comes to the specification of field material allowed in the wall constructions. I mentioned earlier on for slope structures, there are little guidance, and we have to still go back to this federal highway, whereby for wall structures, more or less similar criteria, 15% fines content, plastic index less than 6, a little bit more stringent, okay? In other words, granular fill material. But for slope structures, they have much more relaxation given in the guidance. So the fines content now becomes 50% as opposed to 15%. And the plastic index can be up to 20. So when we talk about soil use, most of the time, these design guidance and code of practice, they have taken a precautionary measures approach, mainly because types of soil in any type of retaining structures or reinforced soil field controls the serviceability limit state. The earlier design discussed earlier was mainly for ultimate limit state, making sure that the structure does not fail catastrophically. So let's have a look how soil affects the serviceability limit state of the reinforced soil. So the first limit, serviceability limit state is the wall deformation. So when we talk about wall deformation, there are a few factors that may cause the deformation, and the red sentences that you can see there all has to do with the types of fill. So presence of a wet layer of soil that, during constructions, creep settlement of fine-grained soil. Okay, again, the plastic index control that, fine-grained soil, the percentage of fines. Swelling of fine-grained soil, simply because with moisture fluctuation, fine-grained soil, is easier to swell and shrink, so causing deformation. There is one factor that may cause wall deformation, which is the creep strain of a geogrid reinforcement. But this is an item that, if you design correctly and adopt the correct tensile strength, the long-term tensile strength, by applying some reduction factors on the geogrid, is quite, easily overcome, basically, as long as you do your homework. The next type of serviceability limit state comes down to wall deformation. And it's quite clear again that, the deformation may be caused by the foundation soil settlement, external loading not considered, and the last two items, the last two sentences are also something to do with the type of fill that you're going to use, i.e. the internal fill soil settlement and creep settlement of fine-grained soil. So in short, the type of soil that you're going to use basically affects more so the serviceability limit state. So precautionary measures is best to be adopted. So I had a summary here. Some relaxation of the fill soil type can be considered for slopes rather than walls. Particular attention to soil PI and fines percentage. These are the two properties that control the swelling and shrinkage of the soil, subject to moisture. The whole idea of a specification is to ensure that a sound and durable, predictable structure's performance in the long term and over a wide range of construction and service conditions, i.e. the serviceability limit state. Okay, we now come to the part where when we talk about a structure, a slope and a wall structures, you can reinforce any angle you want based on criticality of the structure. Even a 1:2 slope, you can reinforce them up to 45 degrees. But these two categories, the 45 degree and the 26 degree, are not the discussion for today's presentation. Just be aware that when you reinforce this slope of 45-degree and shallower slope, you only require some passive facing. When we mention passive facing, there is simply no connection requirement between geogrid and the face. The face is simply whether vegetated or concrete type of surface, using raw type of a matting material without the need of connection. The focus of the presentation on the facing today is more to do with anything between 45 to 70 degree. Some active facing require. Can you read it? You can see from there the type of facings: green terra mesh, the mineral terra mesh, the Gabion terra mesh, and also the 70 to 90 degree category, where a structural facing typically require. Similarly, mineral terra mesh, Gabion. The blue box is the type of segmental block, concrete block facing that I'm going to discuss after this. And the red box, the mesh facing we call it, is going to be discussed by my colleague, Jim. Okay, let's have a look at Keystone TW3 segmental block wall. These are small size dry cast concrete block incorporated with geogrid reinforcement, and there are different type of concrete blocks available in the market. The TW3 blocks that we are talking about in this presentation is what we consider something like a mechanical connection between a geogrid reinforcement to the block system. Okay. And this is by means of making use of a blue color mechanical connector incorporated during the installation, engaging itself with the geogrid type that we're using to create a positive connection. So this is how it looks like. We have the block 450 by 200 high and 300 millimeter wide. It's a small surface area. To improve the connection between the geogrid reinforcement to the face, we incorporate something called polymer connector, which is identified by the blue color connector on the top, in addition to the pin, alignment pin. So why do we bother to incorporate a mechanical connector? And this is one example of a typical failure of a facing connection failure. If you notice closely, these blocks has no hollow core voids. So they are solid concrete, smaller scale size in terms of width. Usually fine, no issue, but for some unexpected forces, such as earthquake, some unexpected forces such as close loading to the face of the wall, moisture fluctuation, you may get some loss in terms of friction, which is what this type of facing is for, frictional connection, and therefore peeling off of the surface failure. When we talk about connection strength, this is how we test the connection strength test between geogrid reinforcement and multiple different types of blocks, basically. Okay, you get a value, you get a data, and this is part of the NCMA method for testing connection strength. A typical mechanical or positive connection strength load looks like the blue line, which is independent of the normal load acting on the geogrid. Whereas a frictional connection will have the strength, obviously, but only when you have quite a high load or certain load acting on top of the geogrid due to the friction between the top and bottom of the geogrid. What this means in actual field is that you are able to utilize much more of the tensile capacity of the the geogrid reinforcement near the face at low overburden pressure for mechanical connector, for positive connection, compared to a frictional connection which relies on higher type of overburden pressure acting on the geogrid, as shown by the envelope here. The next type of concrete segmental block that we're going to show is something called a verti-block. We call them a medium-sized block, which is not too small. It's 1.22 meter by 0.6 meter high and 0.9 meter in depth into the soil side. It is a wet cast concrete with the shear lug at the top of the block, where the next block is going to sit on top, providing the very high shear capacity. Hollow core, much quicker to install, and with 85-degree inclination. This is how it looks like from a plan view. You basically fill up the voids with drainage aggregate and you lay geogrid reinforcement over the block to create the connection between the blocks and geogrid reinforced soil mass. For this type of block, due to the size of the block and the width of the block at 0.9, the weight of the block, there is still connection strength requirement for sure, because this is wall, but due to the shear size, it is less critical compared to the smaller size block when it comes to the need of a positive connection, so-called. Okay. So this is how the geogrid is laid over the entire surface area of the block. After the block is laid with fill up with aggregate in the core, the next layer of block is going to sit in between the shear lug, creating that connection between geogrid and the upper type of block. Okay. This is a reinforced soil presentation, but I thought I'll probably just show this one slide to show that this is a big block. So on its own, it has its own weight. The standard block weighs around 800 kgs, and you can have extended block if necessary to construct the wall up to a certain height without the use of geogrid as mass gravity. Okay. And these are the example of the use of verti-block in one of the job in New South Wales, up to 7 meter high, for an extension or upgrading of the road at the top. Another view of a completion of verti-block. That's it. I think I will pass it on now to my colleague Jim to continue on the double twist mesh facing system or other type of reinforced soil structures. Thank you.
Thank you, Eric, for a great presentation. And I'd like to welcome our third and final speaker, Jim Kounitas. Jim is a civil engineer with over 37 years of experience in the Victorian building and civil construction industries, specialising in contract and project management. Throughout his career, Jim has held several key roles at companies such as Boral, Macquarie and Groundtech. Currently, Jim serves as the sector manager for slopes and walls at Geofabrics, where he oversees commercial sales and subcontracting, which encompasses the design, supply and installation of civil projects, in particular retaining wall systems. Key projects that Jim has contributed to include the Warrigal Road slip repairs for Vic Roads, the spillway for the Victorian Desalination Plant, and the retaining walls for regional rail upgrades. Please welcome Jim Kounitas.
Thank you for your introduction. And further from Alan and Eric's presentation, mine's the final part, basically talking about double twist flexible gabions in the TerraMesh family. And my last slide is more or less on construction costs of some of the various retaining wall systems. Getting into my presentation, I've broken it down to the three TerraMesh families, which are in the Gabions family, but they're really just boils down to the three TerraMesh families into what we call Gabion, your normal Gabion TerraMesh, then your green TerraMesh with green facing, and then your mineral TerraMesh, which basically means it's got a small rock veneer. The first one is the traditional Gabion TerraMesh, which has been around for a while. It's got an integral tail in a 1x1 unit, and most Gabions or TerraMesh units are a 2x1x1 with a 2-meter tail. In other words, it's 3 meters from the face to the back of that end. It's integrated. It typically goes, as you can see there on the slide, between 70 to 90 degree inclination, and it's suitable predominantly for, especially in hydraulic forces. And it's a permanent facing, and it's a 1 meter wide, so it's quite robust and relatively easy to install. As I said to you, there's a little descriptive drawing on your left hand side, which shows the 1x1 and a 2 meter unit with a 1 meter at the face wide, and then a 2 meter tail. So in other words, it's 3 meters from the face of the wall to the end of the tail. And sometimes for higher walls, we introduce geogrids on top of the existing TerraMesh unit. Now, that TerraMesh unit, called that L length, is actually the same material as the Gabion. So it's integrated. So it's got, as I said, a predetermined 2 meter tail or 3 meter overall. However, on higher walls, as shown on that cross section, we can introduce geogrids. In particular, that one there is called the Paragrid. The other two TerraMesh units one is the mineral TerraMesh and green TerraMesh. They're basically the same unit. However, one is mineral being rock, as you can clearly see on the left-hand side there on the little drawing. There shows a little bit of rock facing. And on the right-hand side, it's green TerraMesh. In other words, we put a bit of topsoil there with some seeds, which encourages the grass to grow through the actual face, through the biomac. And predominantly these are the most common angle of these units is 70 degrees. Here's a more detailed information on your TerraMesh unit. The beauty about these systems, there's no additional formwork, no wrapping around of geogrids. There's lesser geogrids because you've already got an integrated 2 meter tail, traditionally between 20 to 35%. And it's a one unit, and basically that's it. And it just gets stapled together with your normal C rings or your hog rings. There's a little table there of a guideline of how many rings you can use per cage, and there's not that many. So a lot of the installers do have their own Gabion lacing guns, or in our case, we do hire them and sell them out. With structures, say, less than 3 meters in height, the actual TerraMesh unit being either a green or a mineral would suffice. You won't need any other additional materials. Just one unit will suffice. In other words, you're only dealing with one product. You won't need any additional geogrids, and it's very, very quick to install. So basically, it comes flat packed. You install it and put it in position, and you just leapfrog it as you're backfilling. The next slide will demonstrate that. This is a particular example we did up in New South Wales, and you can clearly see the terraced green TerraMesh, and you can see the biomac biomac. It's a jute at the face, and that will obviously encourage a bit of topsoil. That also has a geogrid, but in this case, it's a tensile geogrid going to the back of it for that determinant of that height. There you go, what I was referring to. Now you can see in this particular slide, you can see the mineral TerraMesh where we've introduced a bit of rock facing. There's the bracket that determines the 70 degree traditional angle. You can see how it's effective. A lot of people just think it's a full 1 meter wide Gabion, but it's not. It's actually just a 300 mil. And as you can see from the left-hand side, you can see the actual Terra Mesh unit. You can see the bracket. You can see the rock, and then there's a little bit of geotextile, typically bitumen, just behind it to separate between the soil and the rock, so it doesn't mitigate through. With the green Terra Mesh, this is a particular job in New South Wales, and you can see the before shots and the after shots where the grass was encouraged to grow through the actual biomac. A few more photos of various vegetation. Now, vegetation determines also on, the orientation of the Terra Mesh unit, if it's facing particularly the sun and all that. Also, the topography, I suppose, is another better way. But traditionally, the soil that you put in, that little bit of topsoil, if you introduce some sort of seeds, it'll just grow through.
Hi, thank you. Thank you to our great speakers. As always, it's now your turn to get involved. If you could please ask our speakers questions via the YouTube chat box and who your question is directed to. Thank you to everyone who submitted questions whilst registering. I might start off with you, Eric, and we've had a great question that's come in from Clavet, who is watching from overseas. Asking you, Eric, in designing reinforced soil structures, how do current facing systems impact the long-term durability and performance of these structures? Are you able to elaborate on any recent advancements in facing technologies that enhance stability and reduce maintenance needs? Thank you for that question. Eric.
Thank you, Amanda. Thanks for the questions. I think the comment that I'm going to make is probably much relevant to the facing system that we have discussed and shown in this presentation. So all the 5 types of facing systems in these presentations are permanent facings, meaning they have lifespan expectations of between 100 and 120 years required for most of the transport agencies typically. The enhancement of stability comes down to ensuring adequate connection strength for any unforeseen conditions. One particular system in our presentation shown the incorporation of the mechanical connector to create a positive connection between the geogrid and the face. From a maintenance point of view, if you were to consider a vegetative facing, then obviously that part of the maintenance need to be considered, with some kind of a trimming and cutting over time. Otherwise, generally, there is no further requirement for maintenance for all the other facing systems. Thank you.
Thank you. Thank you for that, Eric. And Alan, bringing you into the discussion, we've had a question coming from Robert, and Robert is watching from Victoria, asking you, Alan, what's the biggest mistake engineers make when designing reinforced soil structures? Thank you, Robert.
Yes, pretty good question, Robert. I think one of the big issues in my experience is that you have to start off with the right design method and be very clear in your brief from the client as to what design method they need you to hold by. There are many different design methods, and depending on where your structure is going to be, it could be the Australian standard, it could be RTA methods, it could be MRST methods in Queensland, or some other method. So that's the first thing to establish. Otherwise, you can be going and doing a bit of work that needs to be redone. But in the design process itself, I think recognizing the mechanisms of failure for your particular wall in the particular situation it will be in. And never forget the effects of water. So water behind the wall, water that can seep through the wall, water that can erode the top surface or the front face of the wall, and make provisions for suitable drainage to deal with these sorts of issues, and also add into the wall design any filters that might be required to hold the soil within the wall itself and not let the soil migrate through the facing.
Thank you for that, Alan. A question back to you, Eric. We've had a question that is asking, what is the durability of the GeoGrid and the design life of the system? Thanks, Eric.
Okay. The GeoGrid has most of the GeoGrid that we offer has the British Board Agreement certificate for 120 years design life. So that is because there is the element that holds up the entire stability of the reinforced soil structures together with the facing system. They are normally good for 120 years design life for design typically.
Thank you. And before we jump over to Jim, just staying with you, Eric, I just wanted to ask you, is there any reduction factors that apply for a different brand and series of HSG? Thank you, Eric.
Okay. I assume HSG means high strength GeoGrid. So yes, of course, the GeoGrids are manufactured from different manufacturers, different polymers, and different style of manufacturing. Therefore, they are subject to different polymer creep in the 100 to 120 years design life creep factors, also different installation damage factor, and also different environmental factors. These are summarized in technical data sheets that is quite fairly spelled out and easily obtainable from our website, or simply getting in touch with us, and we'll furnish that information over. No problem.
Thank you for that, Eric. Jim, we've had a question that's come in from Giovanni, who's watching in New South Wales, asking you, Jim, what reinforced soil solutions are available for the private residential market? Thanks, Jim.
Thanks for the question, guys. Giovanni in particular. In New South Wales, from our Moorebank office, we do have available a couple of different options. Obviously, in the residential market, I mean, most of our products can be used in the residential, but traditionally, it will probably be probably our Gabion or our welded mesh Gabions, which sort of cater for that market. Even I've done jobs with a VertiBlock 2 or 3 blocks high in the residential market. So again, it's all about the application. Feel free to reach out to our offices at Geofabrics. We've got offices all over Australia, but in particular, reach out to one of the technical reps in our Moorebank office, and we should be able to put you in the right direction and come up with a preliminary design and some costing associated with it. Thanks, Giovanni.
Thank you for that, Jim. Eric, we've had a question coming from Chichering in Victoria, asking you, Eric. It's quite a long question, so bear with me. What are the most significant advantages of using reinforced soil structures compared to traditional retaining walls? And what are the key considerations when choosing between different types of facing systems, for example, vegetated, rock, architectural for a project? It then goes on to say, what are the latest technological advancements in the materials used for soil reinforcement, and how do they enhance the performance of these structures? Eric.
Right. That is a very long question. If I understand correctly, there are 3 parts to the questions. So I'll try to answer first part first. The most significant advantages of using reinforced soil structures versus the conventional retaining walls obviously comes down to the cost benefit. Alan has presented earlier on there or about 4 meters. Anything beyond 4 meters will definitely become more cost effective using reinforced soil. Besides that, reinforced soil is a very ductile structure. And by ductile, meaning that when you build this structure of a similar given height of, say, whatever, 10 meters high structures compared to a conventional retaining wall, the pressure imposed on the foundation of a similar height will be much more uniform for reinforced soil compared to a reinforced concrete, in this case, okay, retaining wall, and therefore more forgiving in the for bearing capacity considerations. The other benefit comes down to carbon footprint reduction. It has been reported that reinforced soil has 60% reduction in terms of carbon footprint compared to conventional wall. Another benefit comes down to the very high seismic performance due to the ductility of the system. The reinforced soil structures also comes down to reduction in construction time as well, without the need of formwork, without the need of steel reinforcement and concrete and so forth. Lastly, what I can think of is the feasibility for a very, very high structures, and the tallest in the world is 73 meters high that we know of. The second part of the question comes down to, if not wrong, choosing different types of facing. I think we've covered that in the presentation: the cost, the looks, the aesthetics, the speed of installation, location of where the wall is going to be constructed, and availability of good backfill materials, among others. Yeah. The last part of advancement basically comes down to, we mentioned earlier on in the presentation, the engagement of the soil reinforcement to a positively connected facing blocks, so we can maximize the utilization of a reinforcement strength. Besides that, the other advancement in the geogrid reinforcement that I can think of, we didn't cover much time to cover geogrid reinforcement, due to time, is a geocomposite geogrid called Paradrain. There is basically a draining geogrid that basically used for marginal soil fields, typically silt or clay. Or otherwise, because it's just too expensive to bring in quality fields. I have to say the compromise for that comes down to a lot more tests that needs to be done on the type of clay or silt they're going to use, okay? Such as the need for consolidation parameters, expand the volumetric parameters, etc., and also compaction trial tests during constructions. The other compromise that you need to make is basically come down to a slower speed of the installation because of the clay field. Plus, you need time for the dissipation of the pore water pressure to allow pore water pressure to slowly dissipate through the draining geogrid. Okay, I think that's probably what I can say now. If we, this is basically something that's evolving at the back of a reinforced soil technology by utilizing marginal soil fields. Any further information, I guess just get in touch with me. Thank you.
Thank you, Eric. And we are getting a lot of questions for you this afternoon. Our next question is coming from Anis, who is watching in WA, asking you, Eric, what is the optimum backfill height for each geogrid reinforcement layer behind the retaining wall system? Eric.
Yep. Okay. I assume this has something to do with the allowable spacings of the geogrid reinforcement in the face as a structure. So again, referring to the type of facing that we've presented, the and the inclination angle, I would say they would vary between 600 millimeter to up to 1.5 millimeter. For example, obviously, with secondary geogrid in within the 1.5 meters. For example, the green Terra Mesh unit or the mineral Terra Mesh unit that Jim presented can be used to up to 2 unit height due to the double twist mesh length extended from the face unit of 2 to 3 meters, serving as a secondary reinforcement near the face. You use that 2 unit spacing with geogrid normally for very tall structures with high strength geogrid typically.
Thank you for that. Eric, Mohammed has sent a question through this afternoon asking you, Eric, do we need to consider full impact loads as specified table 12.22 AS 5100.2 in the external stability analysis of the wall? Or is there any method to get equivalent static load? Thanks, Eric.
Okay. This is something to do with traffic impact load on what we call a rigid barrier on top of the wall facing. Okay, and in certain code they specify the equivalent static load that needs to be resisted by the traffic barrier, impact barrier, and which is a dynamic load that is converted into a static load type of situation. I think the question comes down to whether we need to consider this horizontal impact load in the design of the reinforced soil wall or MSC wall structures. And the answer is no. This should be a departure. This load, this horizontal impact load, lateral load, should be a departure from the design of the retaining wall, because of the fact that this is an impact load, dynamic load. It's not constantly there. Okay, but again, referring to Federal Highway, there have been documentation that say something like you need to allow for certain additional tensile resistance, tensile load on the top 2 layers of the reinforcement near the impact, maybe near the impact structure, basically. So I have to refer to in terms of what are the increase in the requirement on the tensile resistance and minimum requirement of the length of reinforcement, obviously, to cater for that additional horizontal load. Otherwise, yeah, so this is a very good question. There should be a departure. It should not be considered for the retaining wall design. Okay, and this load needs to be taken care of separately by the parapet or traffic barrier. Thank you.
Thank you, Eric. We have covered a lot this afternoon talking about, in today's Thought Leaders series, reinforced soil structures design and facing systems. So what I wanted to ask all our speakers, maybe starting with you, Alan, and Eric and Jim, just based on your presentations this afternoon, the key takeouts that you would like to leave today's audience with. Thank you. Alan.
Well, I think, Amanda, what I was attempting to cover was the importance in designing reinforced soil structures is to understand initially how they work, understand all the components and how the components act together to ensure a stable structure. But the other critical component of design, especially towards the start of the design, is to understand how your structure can fail, and to go through all of the potential mechanisms of failure and make sure that you're covering all of those in the design.
Thank you for that. And Eric, you covered a lot today. What are the key takeouts for our audience?
I think the key message is that as a company, GeoFabrics, we offer various different types of facing system for reinforced soil. Obviously, not forgetting the different types of geogrid reinforcement up to very high strength. So we have a variety of solutions basically when it comes to slopes and walls. It's impossible for us to cover everything in this one presentation. We have selected a few that is the most commonly used, and we also have different suites of design software for different systems and products that helps engineers and authorities with the problems that they are facing. So yeah, don't hesitate to just get in touch with us. Particularly, I myself deal with the technical assistance side of things more so than the commercial side of things. So I'm passionate about reinforced soil. I'm passionate about slip repairs. I'm passionate about retaining walls. So yeah, feel free to contact. Thank you.
Thank you, Eric. A great presentation this afternoon. Jim.
Okay, thanks, Amanda, and thanks, guys. As you can see from our presentation, we have many systems, in particular with reinforced soil walls, or even as Eric did allude, just some gravity wall systems. Basically, if you have any particular application or a scenario or landslip or any scenario, please feel free to reach out to us. I mean, we have offices all over Australia and also in New Zealand. We do offer a free preliminary design suggestion. And as what Eric just mentioned, we do have proprietary software which we can distribute. They are free, and we can teach you how to use those particular software in designing reinforced soil structures. So again, just to reiterate and summarize, within the GeoFabrics portfolio, Us Guys Slopes and Walls, we can tailor your particular application. So again, feel free to reach out to us. As I said, I'm based in Melbourne, but do look after the East Coast. We do have many engineers all over Australia. So again, feel free to contact us at any particular thing. And thank you, guys.
Thank you, Jim. Nice way to close. It is all we have time for today. Please join me once again in thanking Alan Garrett, Eric Yu, and Jim Kunitas for their time and input. I'd also very much like to thank Engineers Australia's long-standing industry partner, GeoFabrics, for their support. I'm very excited to announce that the Engineers Australia 2024 Climate Smart Engineering Conference is in August this year in Brisbane. Registration is now open, so if you could please follow the QR code on your screen for more information. As always, we're looking for ways to improve, hold sessions that you're particularly interested in. So if you could please take a couple of minutes to complete a short feedback form linked in the description box below. Thank you again for joining us, and I look forward to seeing you at our next Thought Leaders event. Thank you and good afternoon.